Jason Kumar from Hawaii, who will tell us about applying
simulation-based inference to spectral and spatial information from the Galactic Center XS. So thank you very much. And so this is based on a paper which was published earlier in the summer.
We can switch it on, yeah. Let's keep the temperature bit on the high side. Yeah, if that's okay.
I'm for anything. Okay, cool. So as I'm sure many of you know, the Galactic Center XS is an excess of GeV range photons, which are seen from the direction of the Galactic Center by the Fermi Large Area Telescope. And so this has been a long-standing excess. We've known about this for running on 15 years now. But its origin is still a mystery. So one possibility is beyond the standard model physics, and one of the most interesting ideas there is that it could come from dark matter annihilation. So for example, a dark matter particle annihilating to a BB bar final state where the mass is in something like the 30 to 50 GeV range. Another possibility is astrophysics. And again, one of the most studied ideas is that could be a population of unresolved millisecond pulsars. But since this excess has been around for a long time, we're still not sure what the resolution is. It's good to find new ways to shed light on this question of what this origin could be. And so I can briefly describe some of the approaches people have used. One approach is to look at the morphology of the signal. Basically, does the angular distribution of the excess follow the squared density of the dark matter if you assume something like a generalized NFW profile? And that's what you'd expect if this came from dark matter annihilation from an S-wave initial state, for example. Or on the other hand, you could ask, does it follow something like the stellar distribution, which is what you might expect if the origin was millisecond pulsars. Another way you could approach this problem is with what's called the photon counts in pixels distribution. And the basic reason why this would be interesting is that if you think the Galactic Center excess results from a population of bright but unresolved millisecond pulsars, then you might expect this distribution to be somewhat clumpy. And how this would manifest itself is in a non-Poisson probability distribution, because your probability distribution for seeing photons in any particular pixel would be dominated by the fluctuations in the number of millisecond pulsars in that pixel. Now, one difficulty with this kind of analysis is that it's difficult to disentangle the clumpiness you would see from millisecond pulsars emitting photons from the clumpiness you might perceive if you just had mismodeled the background. So I've just highlighted some of the works which have kind of studied this problem using these different approaches, sometimes coming to different results. And these are just examples. There are many more on this. So you can see that this is kind of an active area of research. But one thing we find is that in many of these approaches, you end up essentially factorizing spatial from spectral information. So for example, you might look at the spatially averaged spectrum of the excess. Or you might look at the angular distribution over all energy scales, essentially averaging over the energies. But even if you use both of those, you can lose some of the correlations between the spatial and the spectral information. So for example, suppose the Galactic Center excess does arise from some population of bright but unresolved millisecond pulsars. Then what you'd expect is that each pulsar might produce several of the observed photons. But each pulsar, the spectrum is going to vary from pulsar to pulsar. And so the way this can manifest itself is in a photon energy distribution, which is exhibiting non-Poisson fluctuations, which vary from pixel to pixel. Because in each pixel, it kind of depends on how different the spectra of the pulsars in that pixel are from what the average would be. And so what our goal was to see if there's any way to gain from jointly using spatial and spectral information. Does that help us kind of resolve the origin of the Galactic Center excess? Now, when you use joint spatial and spectral information and you have non-Poisson distributions, it turns out that computing the exact likelihood of your data is computationally intractable. So instead, we want to use some kind of likelihood-free analysis, in particular simulation-based inference. And the basic reason why we want to do that is because it's hard to compute the likelihood of getting particular data because of the combinatoric sums you have to do in partitioning your photons into all the sources that could have produced them. Now, if your distributions were Poisson, then this wouldn't matter. You wouldn't have to actually do the convolutions because the convolution of two Poissons is just a Poisson. But as soon as one of your distributions is non-Poisson, now you have to do the convolutions. And performing those combinatoric sums, that's very hard. But the thing which is easy to do is just to generate mock data. All you have to do is say you have some source distributions, just draw your sources from those distributions, generate photons from each of the sources, assign the photons an energy based on that source of spectrum, and you've got your mock data. So generating the mock data is actually pretty easy. So what our goal is to use simulated data to estimate the posterior without ever having to compute the likelihood. And so for this purpose, we end up using what's called neural posterior estimation. And so the essential idea is to train a neural network to learn the posterior from the data. So the way you kind of train it is you say, okay, I have some distribution of sources, draw some parameters which parameterize the source distribution. Given that source distribution, generate some mock data. And then send that pair, the parameters and the generated mock data, to the neural network, give it a large sample of those, and have it learn how, given the data, to return the posterior on your parameters. And to implement that, we use the SBI package. And again, we just kind of use the default parameters on that. For the machine learning aficionados, the architecture they use is a stack of masked autoregressive flows. And we end up training the neural networks on 10 to the 5 simulations. Although we've tested that, given the summary statistic we're using, that if you use a larger training sample, we've done some runs with a larger training sample, and the posteriors you return are robust to varying the size of the training sample. So 10 to the 5 is reasonable given these summary statistics. Now, what we end up doing is a mock data analysis. So our source distribution models are going to be exact by definition. And so the source distributions we use are for isotropic background, galactic diffuse background, a separate template for the Fermi bubbles, and then the sources of the galactic center excess, which could be dark matter annihilation or millisecond pulsars. Now, when I say our source distribution models are exact by definition, what I mean is you use some parameterized source distributions to train your neural network. You draw parameters from those distributions, get the mock data, train your neural network. Then use the same source distribution for a particular choice of parameters as your true model. You generate some mock data from that, and that's the mock data you analyze. So it's the same source distribution to train the neural network as to generate the mock data you're going to analyze. And the reason we do this is because we want to clarify how much the use of joint spatial and spectral information helps us improve our constraints beyond just using one or the other individually. And in particular, we want to focus on the case where the spatial and spectral data you would get from dark matter versus millisecond pulsars are maximally degenerate individually, where you really have to rely on correlating the spatial and spectral information. And so by using source distributions that are exact, you kind of avoid clouding any of that issue with whether you've mismodeled the backgrounds. Of course, the downside is the mock data analysis doesn't tell you anything about the mismodeling effects, to what extent that is going to cloud your ability to reconstruct the true parameters. And it also doesn't tell you how well your models actually are matching the Fermi data, or which ones are better models for matching the Fermi data. So that's going to be a next step. This is kind of a first step, which is more focused on how much you gain just in principle being able to use joint spatial and spectral information versus using others.
So how much correlation should the spatial and spectral information has to be? What decides that?
You mean, so for example, you mean what decides if there's correlation between them?
Yeah, and how much correlated they are going to be?
Okay, so I'll give you an example. Well, maybe it'll be more clear as I go a little bit further on. Yeah, okay. Okay, so for example, right now what I've done is I've said, okay, we're going to have some source distributions, and I'm going to assume that they're exactly correct. So I have some flux map for, say, the isotropic background or the galactic diffuse background. And I'm going to assume that's exactly correct. I trained the neural networks on that, so that I have a Poisson distributed photon count in each pixel, and I know what the mean is. And then the mock data is the same thing. But if I actually did it on Fermi data, then this could just be wrong. I could have my distribution, which tells me it's Poisson distributed about some value, but in actuality, it could be Poisson distributed at a different value because I just didn't model the background correctly. So I'm not including any of that here. If I did have that, let's say I actually did Fermi data and I've mismodeled that, then some of what, I'm not sure if these results are going to hold. So for example, I might find that using joint energy and spatial information allows me to reconstruct tighter parameters, assuming I modeled the sources correctly. It could be if I modeled a source incorrectly, then that's not going to be the case anymore. And I'll just kind of briefly describe one example of that. So I'm talking about using spatial and spectral information together. The original kind of use of a lot of this non-Poisson template fitting is not with energy information at all, just with directional information. And that was a place where you're trying to see, well, maybe I'm seeing clumpiness in the photon data because I have a bright millisecond pulsar there. So it's a non-Poisson fluctuation of the expected photon counts because I have a few extra millisecond pulsars, which are producing many photons. So that could look like a smoking gun for these millisecond pulsars. But then what people realize is, what if you just spatially mismodeled your Poisson backgrounds? So you just didn't have the mean correct. And so the number of photons you saw is very different from what your source distribution told you could see. You interpreted that as a non-Poisson fluctuation, which is a millisecond pulsar. It could be you just mismodeled the background. So that's one of the ways in which the results you get from this could be clouded if you've mismodeled your background. And in this analysis, I'm not going to be able to address that because I'm going to assume the backgrounds are modeled correctly because I just want to see how much I gain from adding spectral to spatial as opposed to whether spatial itself gets confused. I'll discuss a little bit why you might think this is going to be helpful even when you have mismodeled backgrounds. But again, that's just something where the proof is in the pudding. So that's going to be a next step. And so the first step of our analysis is with generating photons. Where our analysis begins is generating individual photons. And so the photon generation steps are, let's drink some water for a second. For the Poisson distributed sources, like say, the diffuse backgrounds or dark matter annihilation, you start with a high-resolution pixelized flux map. So in each pixel, you can use the flux to draw the number of photons you should get from there. You can assign each one of them an energy based on the average spectrum in that pixel. But for the non-Poisson distributed photon sources, like those coming from millisecond pulsars, we start by generating the pulsars themselves. So you draw your millisecond pulsars from some density and luminosity function. So each pulsar has a luminosity. You draw its spectral parameters from some distribution. And then for each millisecond pulsar, given its luminosity, you draw the number of photons you've observed. Each of those photons, you assign it an energy from the spectrum of that individual pulsar. And then what you're left with is just a big list of photons with true energies and true directions. And then for each of those photons, you vary its energy and direction using the instrument response function, essentially the energy and angular resolution. And your output from this is going to be a lower resolution pixelized count map in each energy bin. So number of photon counts in each pixel within a given energy bin. Now, one thing I'll mention here is the fact that you start with generating individual photons allows you to correctly treat the energy dependence of the point spread function. So that's essentially the angular resolution, and that's going to vary with energy. But since you have the true energy of every photon, how much you smear its direction, you can correctly implement based on what the energy of that photon happened to be. And so now we have to say, what are our background source distributions? So for the diffuse astrophysical backgrounds, that's the anisotropic, the isotropic background, and a separate template for the Fermi bubbles. For the diffuse anisotropic background, we use model O from this Bushman et al. Paper. For the isotropic background, we just use the Fermi-Lat model. And for the Fermi bubbles, the spatial distribution we get from the NPT-FIT tool, but the spectrum we get from Su-Slat-Ira and Finkbeiner. So you can see we've kind of mixed and matched all of these templates. But for our purposes, it doesn't really matter because this is a mock data analysis anyway. By definition, these are going to be correct. As long as they're roughly good matches to what you see in the Fermi data, it'll serve our purpose as the background for asking our question of what happens when you add onto that a galactic center contribution from either dark matter or millisecond pulsars, and can you tell what you added onto this? And I'll mention here that for these templates, there are no floating parameters. We just take the normalizations which these authors found and try to fit their model to the data. Now, for the millisecond pulsars, the first thing we need is the spectral distribution. And so for that, we extend some work of Cholas et al. And what they did is they found 61 pulsars, which at the time were identified by Fermi-Lat and gamma rays. And they fit each of them to a spectral form, which is a power law times an exponential. So there are two parameters, alpha and ECAT. So they end up getting 61 fit parameters with uncertainties. And what we do is we use those 61 fit parameters to estimate the probability distribution for the two parameters, alpha and ECAT, using Gaussian kernel density estimation. And so this is basically the probability distribution you end up getting for those parameters from this. Now what I've plotted here in these kind of light purple lines are 30 spectra, which are randomly drawn from this probability distribution. The line in black here is the average you get from many spectra drawn from this distribution. And the purple, the solid kind of purplish line here is the best fit of the galactic center excess to this functional form, again, done by Cholis and company. And so what you can see is that, one thing is that this average millisecond pulsar spectrum, at least visually, is not that far away from the galactic center excess. So you can see why pulsars might be a good explanation for the galactic center excess. But kind of the main point I also want to illustrate is the large variation in spectra you get going from pulsar to pulsar. So there's significant variation there. You also need the millisecond pulsar luminosity distribution. And we use a parameterization, which is a broken power law form. So essentially the parameters you have are the two power laws, the breakpoint, and the overall normalization. But the only one we're going to allow to float is the overall normalization. We're going to look at a couple of models where we fix the other parameters. So one choice we're going to use for a model for the pulsars is from Lee and company. And so these are kind of the parameters they find for the power laws and the breakpoint. This is a model they kind of use to explain some of the early non-Poisson template fitting analyses, where you saw a lot of clumpiness in the photon spectrum in the Fermi Large data, and you want to explain it with millisecond pulsars.
So what is the physics motivation behind introducing this LV, so this broken power law?
I'm not sure there's really much of a physics motivation. As I'll mention, this isn't the only luminosity function people use. Other people use a log normal, for example. Now, to say which one is better, or whether either are any good or are motivated, would require more astrophysics than I know. But as near as I can tell, this is something where basically people just say, let me look at the pulsars I see, in the galactic plane, in the clusters. Do either of them fit reasonably well to this, to these kind of forms? Now, this particular broken power law, you can see there's a steep fall off above the breakpoint. And you can kind of see roughly why they wanted to do this, because you want a lot of clumpiness just below the point source threshold, because you don't want to be able to, because you shouldn't have seen a lot of these. So you need to have clumpiness, a lot of bright ones just below the point source threshold. So that kind of motivated this choice here. Okay? Now, and in that choice, what you'd find is that to produce the full galactic center excess, you'd need 650 pulsars. We're going to treat that as a floating parameter, and this would be when you've maxed out and you've explained the entire galactic center excess. Now, an alternative model we could use was one which Bartels and company showed, and that's one where you have many more faint pulsars. So in this case, you have a much less steep fall off above the breakpoint, and now you need 30,000 millisecond pulsars to produce this. So this provides you with a much, many more pulsars producing this. And I'll describe a little bit some of the reasons why one might favor one or the other a little bit later on.
I'm a bit surprised that number is floating so much. Is there any consistency check with neutron star population synthesis within the...
There are more consistency checks than you can shake a stick at. They all lead to different results, which people argue about. And I'll describe a little bit of that later on. But there are ways in which people try to estimate this. What are good, what are not. But part of it is, you can estimate it looking at what you see in data, but who says that what you see in data is representative of the galactic center? So, yeah, it's like, well, okay, maybe when I get to that slide, I'll get back to that question. Now, you also need the spatial distribution for millisecond pulsars. And for that, we're going to actually need the dark matter distribution as well. Because what I'm going to assume is that millisecond pulsars are distributed according to the dark matter signal. So they have the same spatial distribution. The reason why I want to do that is because I want to focus on the case where the spatial information is as degenerate as possible. So for the dark matter, I'm going to assume it's distributed according to a generalized NFW profile. Now, the scale radius of the Milky Way halo is like 20 kiloparsecs. We're only 8.5 kiloparsecs away. So basically, we're in the inner slope region. As far as we're concerned, it just goes like r to the minus gamma, where gamma is some power. And I'm going to assume it's 1.2. I'm going to fix that because when people look at dark matter origins for the galactic center excess, this is what they find is a good fit to the data. So if I assume S-wave dark matter annihilation from an S-wave initial state, then your dark matter signal is basically distributed as the density squared. I'll assume that millisecond pulsars are also distributed exactly the same way. Now, of course, that's not necessarily realistic. I could use more realistic pulsar distributions, things which follow the progenitors of millisecond pulsars. And that's especially important if you want to do this on real data, because that's what real data could follow. But since we're doing a mock data analysis whose point is to focus on making them as degenerate as possible, for our purpose, it's good to just make it exactly the same as dark matter, just to see if I can use spectral information to tease out the difference between those two.
So in general, the millisecond pulsar shouldn't be distributed rho square.
In general, how they're distributed shouldn't care about the dark matter distribution at all necessarily. Even if it did, there's no particular reason it should go as rho squared. Right? So the reason why I'm doing that is to say, well, let's say it's distributed like the stars instead of like rho squared. Then that will give me a way to distinguish between the two. And people have already done a lot of that analysis. That's kind of that morphology. And they've kind of, there are different views on that, on what the result of that is. But what I want to see is, let's say I can't use that as a handle. I can't say that the pulsar spectrum looks different from the dark matter spectrum. They just look as close as they can as possible. Can I still use the spectral information to tell the difference? That's kind of the idea of this. Now, there are also going to be disk pulsars. But we're going to end up masking the galactic plane. So they're not going to contribute much to the galactic center excess once I've done the masking. And so they have little effect on the galactic center excess. The posteriors don't really constrain them aren't really constrained. So we're just going to end up marginalizing over this source. Now, the last thing I need is the dark matter spectrum. And so I'm going to consider two models for that. In one model is one of the standard ones people use for dark matter annihilation. It's dark matter annihilating to BB bar. Here again, I've reproduced that figure I had from the spectrum millisecond pulsars. But the dashed lines is the spectrum you'd get from dark matter annihilation to BB bar if your mass was 10, 30, or 70 GeV. And so you can see in the 30 to 50 GeV range, this spectrum you get from BB bar annihilation that's similar to galactic center excess, similar to the average millisecond pulsar spectrum. They're all kind of similar. You can see how they could be responsible for the galactic center excess. But again, by eye, you can see that there are differences between them. You can tell the lines are a little bit different. So the alternate model I'm going to use is where I just take the dark matter annihilation spectrum to be exactly the same as this average millisecond pulsar spectrum. Okay? Just to see if I make the spectral information as well as the spatial information as degenerate as possible. Can I use the joint information to somehow distinguish between those possibilities? Okay. So having gone through the various source distributions we have, we can now just talk about the data itself. And so the region of interest we focus on is within 10 degrees of the galactic center, but masking within 2 degrees of the galactic plane. And the energy range is within 2 to 100 GeV. So we break this up into 280 pixels and 10 log spaced energy bins. So when you pick a choice of your parameters for our various source distributions, generate your mock data, the output you would end up getting is basically a flux map like this for the number of photon counts per pixel in each of 10 energy bins. And in one energy bin, this is just one realization from one mock data set. But you don't want to feed 10 of these to the neural network because then it's a high dimensionality piece of data, so it takes a lot of computational time to train the neural network. So instead, we want to compress to a summary statistic. And we use 3 different summary statistics depending on how much information, what types of information we're using, to see if using different types of information can give us an improvement. So in the case where we use energy and directional information jointly, the summary statistic we use is an energy-dependent histogram of photon counts per pixel. And this is one example. Basically, the number of pixels which have a certain number of counts in a certain energy bin. So this is just one summary statistic you get from one mock data realization. In the case where you only want to use direction information, it's just a histogram of photon counts per pixel. Essentially like this, but assuming you just had one big energy bin from 2 to 100 GeV. And in the case where you only use energy information, what you have are basically the number of counts per energy bin summed over the entire region of interest, so averaging out all the directional information. And so having done this, we can now start with a mock data analysis. And the first mock data analysis we'll use will have a dark matter model and a millisecond pulsar model. The dark matter model is going to be annihilation to BB bar. So the parameters are going to be the dark matter annihilation cross-section and the mass of the dark matter. They both determine sort of the magnitude of the signal, but the shape of the spectrum is also determined by the mass. For the millisecond pulsar model, I'm going to use that first broken power law model where the full galactic center excess will be generated by 650 millisecond pulsars. And so the idea is that you train your neural networks against these two models, and then you generate mock data using one of three choices for what the true model would be. And in one case, the true model is galactic center excess is dark matter only, assuming the mass is 30 GeV. In the other case, it's millisecond pulsars only, so the number of pulsars in the core, that's what a core is at 650. And then the third case is when it's 50-50. So you have half the dark matter annihilation cross-section and half the number of millisecond pulsars. And in each case, you've trained neural networks using one of three different summary statistics, either using energy and directional information, or just energy information. And then you see if you can reconstruct the true parameters. Now the green curves are using joint energy and directional information. Unfortunately, it's kind of hard to see inside in the 2D histograms because it's inside the red and the blue. It's easier to see the effect in the 1D posteriors, where you can see that using energy and directional information definitely improves on your ability compared to either one individually, and it lets you reconstruct what the origin of the galactic center excess was. But one thing you might notice is that even if you just use energy information alone, you can pretty much tell what the origin of the galactic center excess was. And the reason is because we assumed we knew the spectrum of dark matter. We knew our source distributions, I should say. So we knew the average millisecond pulsar distribution. We knew the BB bar distribution for any of these masses. And as we can see, even looking by eye, they are close to each other, but we can see visually they were distinct. And there are a lot of photons coming from the galactic center. So that tells us that we had enough statistical power to distinguish those possibilities. But that's not really realistic because we assumed we knew the source distributions exactly. So we assumed we knew the average millisecond pulsar spectrum. Okay, and who knows that the Cholis sample of 61 is good enough to tell us that. We assumed that we knew dark matter annihilates at BB bar, but who knows that that happens with 100% branching fraction. Maybe it goes partially to tau tau bar or something else, right? So to hang your hat on just knowing those fine details in the differences between the spectra is probably not realistic. So the next analysis we did is where we used the same millisecond pulsar model, where the full galactic center excess is generated by 650 millisecond pulsars. But for the dark matter, we assume that the annihilation spectrum is exactly the same as the average millisecond pulsar spectrum. A core is the number of pulsars in the core. So for this model, if a core, you can think of that as normalizing the luminosity and density function to how many millisecond pulsars are there. And so if there are 650 in the core, for this model, that's enough to generate the full galactic center excess. So that would be the true model in the case we had millisecond pulsars only as the origin of the galactic center. Now for dark matter, now I really only have one parameter, which is annihilation cross-section over dark matter mass squared. Because those together determine the number of photons I produce. The spectrum doesn't care what the mass is because it's set to be the average of the millisecond pulsar spectrum. Now in that case, you'll notice something a little bit interesting, which is even if I use energy information only, I can still reconstruct, my true models are dark matter only or millisecond pulsar only. Even if I only use energy information, I can still kind of reject the wrong model. I can figure out if it's only dark matter, it's not millisecond pulsars. If it's only millisecond pulsars, it's not dark matter. And that might seem kind of weird because I'm only using energy information. I'm not using any clumpiness of the spectrum, or clumpiness of the signal. I'm just using the energy spectrum, and I've set the dark matter spectrum to be exactly the same as the millisecond pulsar average spectrum. So how can I tell the difference? Well, if all the pulsars had the same spectrum, then I couldn't tell the difference. It'd be completely degenerate, and there's nothing I could gain from that. Because the pulsar spectrum can vary from pulsar to pulsar, what I'll see is that the energy distribution is going to exhibit non-Poisson fluctuations, which come from pixels happening to have some pulsars whose spectrum is very different from the average. And we saw there can be a significant variation. So that's what leverages this. That's entirely due to the fact that the pulsar spectra is not just the average spectrum. It's varying significantly around the average. Now you can also see if I just use directional information, I also get some ability to reconstruct the origin of the galactic center excess. And that's consistent with other analyses which have looked at the case where you've correctly modeled the backgrounds. But you can see that when you use energy and directional information together, you get much tighter constraints. Now, one thing I've done by compressing to these summary...
Can I ask a dumb question?
There are no dumb questions, only dumb answers.
Can there ever be a situation in which even the dark matter energy spectrum could vary?
Yeah. So, I'm trying to think of a good one where the dark matter spectrum can vary. Sure, oh yeah. Let's say you had some multi-component dark matter. And the distributions are not the same, because they don't necessarily have to be the same. So that'd be, I'd say, the easiest example where that could happen. So if you wanted to do that, again, you could do that with more templates. And there you'd say, I'm not just relying on the fact that it's varying, but I'm relying on the fact that millisecond pulsars vary in one way, and this dark matter model is varying in a different way. So that's what you'd have to rely on. Yeah. Now, in compressing to a summary statistic, we've gained computational efficiency, but we've lost some information. And one thing in particular we've lost is correlations between neighboring pixels. And where that can be important is if the point spread function smears photons from one pixel to a nearby pixel. Okay? So we can count essentially how many bright pixels we have in a certain energy bin, not necessarily if they're nearby, which could be what happens if you have a millisecond pulsar in one, and then the angular resolution kind of smears those photons into another one. And so that is something we can kind of discuss a little bit, we'll get to a little bit later. Now, again, I kind of focused on this, the millisecond pulsar model I've used so far has been that one where 650 millisecond pulsars are what generate the entire galactic center excess. But again, kind of a point which is made is, why do we take that? How do we know that that's what it's going to be? That model was motivated by some of these ideas where people said, okay, I've got this non-Poisson template flit. I see all this clumpiness. What kind of millisecond pulsar model can give me that kind of clumpiness? And that was kind of a good fit because you had a lot of unresolved pulsars, or not very many, but a few bright ones just below the point source, the point source threshold. So that could be giving you a lot of clumpiness. But what people have realized is that, well, who knows? Maybe that's not quite right. If you mismodel the backgrounds, you might see some clumpiness where maybe there isn't clumpiness. Maybe we shouldn't take all that clumpiness to the bank. So what are other ways we could estimate that? Kind of what some people have concluded is that it might be a lot more than order 1,000 millisecond pulsars. So this kind of gets back to that question of how do we motivate any of these distributions? So I'm going to focus in particular on some work from Holst-Tupper and company back earlier this year. So what they assumed is that galactic center millisecond pulsars have the same luminosity function as millisecond pulsars in the field, which basically means in the galactic plane. And they use a log normal parameterization for that. So what they say is that if you do that, if you say that that log normal parameterization has to be consistent with what we see in the galactic center, has to be consistent with what we see in the galactic plane, then you'd need at least 36,000 millisecond pulsars to produce the entire galactic center excess. But if you did that, you should find at least 20 in the galactic center, which should be identified as actual point sources. But you only find 3. So they'd say that scenario is excluded at 3.4 sigma. That's what they would say.
Is that the missing pulsar?
I'm not sure if they call that the missing pulsar problem, but that would be one example of that, yeah. It would be missing pulsars. I'm not sure if that's what people refer to a missing pulsar problem, yeah. So how could you get around that? Well, one way is, let's say you just change the normalization. You said it's the same luminosity distribution, but you just have fewer millisecond pulsars. Only 40% of the galactic center excess is produced by these millisecond pulsars, and the rest comes from something else. But then you could have the same luminosity distribution as the ones in the galactic plane. On the other hand, you could also say that I have, the full galactic center excess is produced by 200,000 millisecond pulsars, but they're a factor of 5 fainter than the ones in the galactic plane. Okay? Now, so those are a couple of possibilities. Now, recently, and by recently I mean I think within the past week or two, Amario, Linden, and Hooper did a similar analysis, getting similar results for millisecond pulsars in globular clusters, saying basically that if you have the same distribution, it has to either be not the whole galactic center excess, or it has to be systematically fainter. Now, why does it matter to use globular clusters? Well, again, that brings back to the question of why would millisecond pulsars have a different luminosity function in the galactic center versus in the plane? Well, if you asked for reasons, one reason you might say is, well, you expect pulsars in the galactic center to be older than pulsars in the plane. So maybe the older ones have a different luminosity function. But globular clusters also are expected to have older millisecond pulsars. So what you might have thought is, if the luminosity distribution in the galactic center was systematically different than what it was in the plane, maybe it would match what it was in globular clusters, and that might give you evidence for that. Well, it turns out that's not what you see. It seems that what they found is that actually what you see in the globular clusters is similar to what you see in the plane. It wouldn't help you explain the full galactic center excess. Then again, Plogan Company, which involves Chris Gordon, who is Ian's advisor, they kind of did a similar analysis between millisecond pulsars in the galactic plane and millisecond pulsars in the galactic center, and they find there's no tension. So they don't find a 3.4 sigma tension. So I'm not exactly sure why their analyses are different. But from my perspective, none of that was really so much important, whether how those analyses match or not. It's just that the point would be that if I try to derive the distribution of luminosities for pulsars in the galactic center using what I observe in the galactic plane, it tends to give me a number which is much larger than 1,000. Okay? If I just use the galactic center excess, there's only 3 in the galactic center, so that's not enough to tell me anything. I have to draw from somewhere else, and if I can either say I don't know what it is, in which case make it a broken power law, whatever you want, right? Whatever you have no idea. Or if you say, well, maybe I can derive it from these other sources, then whether you use broken power law or log normal, it seems to push you to a larger number of millisecond pulsars. Now, why that matters is that if more millisecond pulsars are responsible for the galactic center excess, then you're going to see fewer photons per millisecond pulsar. Okay? In particular, the galactic center excess is only ordered 10 to the 4, 10 to the 5 photons. So around the order of millisecond pulsars you might have here. Which means this is going to start looking much more Poisson. And as we saw, where this correlation between energy and angular and spatial information becomes important is when it's non-Poisson. So does it still help you to use that information as you make these count distributions more and more Poisson? Now, as you can see, a lot of these works kind of came out after our preprint, which was back in February. So we didn't really address these specific models. But we did address that alternative pulsar model, which in some ways is similar to this. Again, it's not quite the same. It uses a broken power law instead of this log normal. But that was a model where the full galactic center excess comes from 30,000 pulsars. So again, you expect things to be much more Poisson. So you can, again, analyze that kind of a system, train the networks against those two models, and feed in, analyze mock data generated from a true model where it's either dark matter only or millisecond pulsars only, which are generating the galactic center excess. Again, assuming their spectra are as degenerate as you can make it. So the dark matter spectrum is the same as the average millisecond pulsar spectrum. What you see is that directional information alone basically doesn't tell you much of anything. It doesn't really help you constrain anything. But if you add energy information, you can now again reject sort of the wrong model. If it's a dark matter only origin to galactic center excess, you can reject it being no dark matter or vice versa. So you can see that even in this case where it's much more Poisson, you still have enough correlation between energy and spatial information that you can get a handle on what the origin of the galactic center excess could be. Now, another thing you can ask is, how biased is our parameter reconstruction? So you can say, if you reconstruct parameters from your posterior, how biased is it from the true model which you put in this mock analysis? And so the way we do it, we analyze this, is we generate 100 mock data samples from the same true model, which was 50% dark matter, annihilating to the average millisecond pulsar spectrum, 50% millisecond pulsars, which amounts to 325 millisecond pulsars. So half of the full normalization of our original pulsar model. Now, all you do then is you just kind of get your reconstructed parameters, find the mean and the variance of the mean, and see if that is biased compared to the variance in the mean, compared to, with respect to the true model. And what you do find is that there is a bias, but the bias is small compared to the 1D confidence interval, or credible interval, on a single data realization. Okay? So on a single analysis, your uncertainties are large compared to the bias in your reconstructed parameters.
Mm-hmm. Why is that if I just take the energy for the A code, the peaky shifting towards the left?
You're saying why the energy is shifted?
Yeah.
I think it's just because you don't have much of a constraint. So basically, this can't really, the energy information can't really tell anything here. So basically because you have enough millisecond pulsars that the energy information alone can't, kind of smooths out the average. The directional information alone smooths it out. But it's the correlations between that which gives you a handle on it. So another example you can look at in terms of bias is to see how much the bias changes because we modeled the instrument response function correctly. And so remember, the way we modeled the instrument response function, both in training the neural networks and in generating the mock data to be analyzed, is you said for each photon I had its true energy, I varied its direction based on the angular resolution, which is a function of that energy. So
So what is this bias actually? I mean, how do we quantify it or where do we see it?
So how you would quantify it is you'd say, okay, let's say I did 100 mock data analyses of one of these true models. So each one I return a maximum of the posterior. And I want to say, so I've got a mean posterior. Each one gives me a posterior. I take the mean and the variance of the mean. So that'll give me a mean plus an uncertainty. And I say, how far away is that from the true model compared to the variance in the mean? So if there was no bias, what I'd say is that the variance in the mean keeps dropping, but the difference between the mean and the true value keeps dropping too. So I would always find that the true value is within the variance of the mean. The difference between the true value and the mean would be within the variance of the mean. Okay, if I didn't really have a bias. In our case, you find that there is a bias if you do 100 of these samples, in the sense that the difference between the mean and the true value is greater than the variance of the mean, but it's small compared to just the variance of a single realization. So there's a bias, but it's not a bias which is noticeable in a single data analysis, which is what you do if you just have Fermi data. So again, you can try the same game in which you say, let me use these same 100 mock data samples I generated by correctly modeling the instrument response function, but just analyze them with a neural network where I incorrectly modeled the instrument response function. So by incorrectly modeling it, what I mean is let me train the neural network where I apply the point spread function, not using the true energy of the photon I'm applying it to, but just using the average of the pulsar spectrum. So I've kind of trained the neural network as if I didn't have the individual photon information. But then I'm going to analyze real data where the angular resolution depends on the true energy. And you can see, how does the bias change? And it turns out, again, the bias doesn't change, the change in the bias is small compared to the uncertainty in a 1D posterior for a single data realization. And so that was the effect we were interested in. It ends up being small, and that's kind of an effect of using a large pixel size. We only have 280 pixels. And so what that kind of means is that unless your pulsar is near the edge of the pixel, it doesn't really matter how you implemented the point spread function, because the photon, however you smear it, it's going to still end up in the same pixel. So where this could be more relevant is when you have more pixels which are smaller, and also when you keep pixel correlations and use a summary statistic where you keep those correlations, and you can see the smearing of a photon from one pixel into a neighboring pixel. And so last I can describe some future work. So as I mentioned, what we did is a mock data analysis where you assume you've correctly modeled the source distributions. But what people have found at these non-Poisson counts and pixels distributions analyses is that the analysis becomes much more complicated if your source is mismodeled. Basically because it's hard to distinguish the effects of a non-Poisson fluctuation in a source which you've correctly modeled versus a source situation where all your fluctuations are Poisson, but you just didn't model the source correctly. Now, one thing you might hope is that jointly using spatial and spectral information could be more robust to this. Okay? So it's not something we've not tested, but it's something you would hope would be true. And the reason you might think it's true is because, if let's say you have clumpiness, which is due to having, millisecond pulsars, which are generating multiple photons, their spectrum is going to vary from pixel to pixel in a way which is different from what would happen if you just mismodel some diffuse astrophysical process. So that's something which you might hope would help you get a handle on the mismodeling question, which is something we haven't addressed yet. But again, that's just a next step, which is to try to train, essentially implement mismodeling of the backgrounds in kind of a similar way of training the neural networks with a mismodeled background, and then inputting data with what is your true model for the background to see if you can still figure out whether what you added onto it was pulsars versus dark matter annihilation. Other things we can use are looking at different summary statistics, maybe some which throw out less information, other machine learning algorithms beyond neural posterior estimation. And after that, what you'd like to do is analysis of actual Fermi data. Another track on things we're looking at is just applying this as a general purpose photon generation tool for interfacing with simulation-based inference, and in particular applying that methodology to the diffuse gamma ray background. So the diffuse gamma ray background is another thing like the galactic center excess, where we don't really know what the sources of it are. Okay? Likely sources include diffuse galactic emission from astrophysical processes in the Milky Way, including dark matter annihilation. Unresolved galactic point sources, which could be unresolved pulsars, dark matter subhalos. Also unresolved extragalactic sources, which could include things like blazars, misaligned AGNs, star-forming galaxies. Now, since some of these are unresolved point sources, where you could be producing multiple photons, you can again ask, can correlations between spatial and spectral information help you quantify what are the sources of the GGRB? So that's upcoming work with Ian, who gave a talk here yesterday and is in the audience today, and with his advisor, Chris Gordon, which is essentially applying simulation-based inference to the DGRB. And as part of this, involved generating what will be a publicly available tool called AEGIS, which is the Astrophysical Event Generator for integration with simulation-based inference. And what this is basically a tool such that, given the spatial and spectral distribution of your sources, it just generates photons for you, generates mock photon data, including the smearing of the energy and the direction using the instrument response function. And so with that mock data, you can then interface that with any kind of simulation-based inference algorithm or tool, okay? And can use it, for example, analyzing the galactic center excess, the DGRB, or whatever other gamma ray source you're interested in. And so that's some upcoming work. And finally, rather than conclude, I was just going to briefly remember my colleague and one of our co-authors on this paper, Eric Baxter. As some of you may know, he passed away this summer, shortly before this paper was published, but he's in our thoughts. I'll end here.
More questions? I have a question.
Mm-hmm.
Is it possible to distinguish between dark matter and NSPs by using data below GeV, say at 11 G or 100 LV?
Yeah, so you could do that. With Fermi, it gets a little harder because the Fermi effective area changes, varies rapidly with energy below there. So it becomes harder to correlate those, but one could try to do the work and do that also. Integral goes to too low energy. So the thing is, once you go below Fermi's sensitivity, you get into what is broadly called the MEV gap, which is basically where you say beyond ERID and COMTEL, you haven't done anything. So there's been no new instruments since there. So people have all these proposals like COSY, EASTROGAM, Amigo X, all these things which are supposed to fill in that gap. But when that happens, you can use that as well. But no.
Once those are implemented, is it possible, will it be possible to distinguish between NSPs and
Again, I'm not sure I have a complete answer to that because we haven't studied it. But what I would say is that if you look at kind of all these spectra, did I pass it? Yeah, if you look at all these spectra, even forgetting the differences between them and how whether they'll be more different or more similar at lower energies, you can just see you're expecting more photons at lower energies. So of course your backgrounds are also increasing at lower energies, but one way to think about it is you're just getting a lot more photons. So if there's more data, if there's more to be extracted from there, you're getting more photons to see that. Now, it doesn't help you that much with Fermi because although you're getting more photons, that's where your effective area is decreasing. So you're not necessarily seeing more photons at Fermi. But at some experiment where that's not the case, then you might benefit.
So one very quick question. So the definition of bias, what you say. So if we have a mismodeled case, so in that case, will the bias be different from the actual case?
Oh, if you've mismodeled the background, right. In general, it could. So what I would say, the definition of bias, I would say, would be the same, but with the actual bias, it probably could. So I guess the idea would be to say, if you mismodeled the background, could you see a bias? Right. Now, I can describe it in terms of some of these analyses which only use directional information. What they find is that it does. So one thing which people, I think, did is you'd say I do some analysis and I recover some point sources. So it tells me that I have clumpiness, I have millisecond pulsars, that's what's generating this. Now let me just throw in a dark matter model, okay? And then do the analysis. So I've just thrown in data, which is from dark matter, and it absorbs it into millisecond pulsars. So that would be an example of a bias, because that you have a true model because you've just plugged in photons from dark matter annihilation, and it's telling you it came from point sources like millisecond pulsars. And the reason it ends up doing that is because you mismodeled the background. And so the idea is that it keeps saying, you've got a bunch of millisecond pulsars here because I'm seeing a photon count which is much larger than what you'd expect if I just looked at the mean Poisson distribution, but just because you had the mean incorrect. So it might have been a Poisson distributed source, like say dark matter annihilation or whatever, but since you didn't know what the mean was, it interprets it as some non-Poisson fluctuation. So that's one example where mismodeling can lead to a bias like that. Now, when you include energy or directional information, you might hope that it would be more robust to that, because you'd say, now I can use the spectral information and see, do I see millisecond pulsars whose spectra vary like millisecond pulsars should, as opposed to just the average, which is what you get from dark matter annihilation or something. Maybe it will, maybe it won't. That's something we just have to do and see. I think there's one more here.
So I don't know much about these things. So couple of questions, very basic questions. So this galactic center axis is coming from mostly the bulge, right?
Well, it goes out to order 10 degrees or so well beyond the bulge.
But it's mostly spherical and it's not located on the disk.
Well, when you say it's mostly spherical, that is a bone of contention. So there are some people who will say it's a very good fit to a spherical distribution. There are another set of people who will say, well, actually, it's not really a good fit to spherical distribution. It's much more a fit to what you can describe as a boxy bulge distribution. So take a galactic bulge-like distribution along with the boxiness of it, because it's like a bar-shaped thing. And that kind of a distribution is a much better template, some would say, than the generalized NFW square template. So there are lots of back and forth between all these groups on which is a better fit to that. Okay? And I won't get into, honestly, I don't know enough to state a strong claim on that.
So the 511 keV line is not a part of the galactic center.
No, that's not, because that's at 511 keV. This is all seen by Fermi. So Fermi can't even see that. This is all seen by Fermi in the GeV range. Yeah. The 511 keV excess, that is there, but that would not be addressed by this. I mean, I should clarify. If there's some dark matter annihilation process, it could also generate that. Because you could say that I have some dark matter annihilation, it generates photons. There's some process which also generates positrons. Those positrons slow down, and then they annihilate with electrons and produce 511 keV. So they could be related, but it's just not this excess.
In the galactic center axis, you see it from every galaxy, or it is only from the Milky Way?
Galactic center excess is from the Milky Way. Now, there could be excesses from other galaxies. So for example, M31, they see an excess from M31. For other galaxies, I think it's just too far away to make a solid statement, because again, you need to know something about the backgrounds in order to say that there's an excess. So for M31, it's close enough that you can estimate the backgrounds and make some claim that there's an excess. I think for other galaxies, it's too far away, because your signal's going to fall off like 1 over r squared. You need to know the background, so it becomes a harder analysis.
Because I was thinking, if it's sourced by millisecond pulsars, then the intensity will have a z dependence. If I go farther back in time, then the galactic center axis will decrease.
Right, but the thing is, if you're going back that far, then there's no galactic center, right? Anything which is non-trivial z, everything, the whole thing is just a point. Yeah.
So the diffuse gamma ray background instance of what energies?
The diffuse gamma ray, in principle, it can extend all the way to like Hawk energies, right? But that's not necessarily where you'd be interested in. We only went up to 100 GeV. But in principle, you got processes which go to TeV range. Yeah.
So, and how exactly would a millisecond pulsar emit energy?
I can't give you a great estimate of the astrophysics of that. I think there are various. I'm not sure people really have a great idea. I think a lot of it, I shouldn't say that. I should say I think they have multiple great ideas, and it's not obvious which is the best idea. But I think, ideas are, well, you have these jets which come off. If those jets accelerate leptons, then those leptons can inverse Compton scatter off various things, so that's one idea. But is it only leptons? Does it also accelerate, protons or something like that? I think that goes well beyond my knowledge of how these things emit. You could have dark matter sitting in the millisecond pulsar, but then I'm not sure why it would just sit in millisecond pulsars, right? It could sit in all sorts of things, yeah. Mm-hmm.
I think there's a paper. Captured only the
yeah. Yeah. So one reason why they want it to be millisecond pulsars is because the millisecond pulsars are processes which can spin them up, so they have more energy which they can radiate out in gamma rays. But again, I think that goes more on the astrophysics side of particle astrophysics, and I'm much more on the particle side, so yeah. Mm-hmm.
Can radio observations nail this in some way or the other?
Radio observations can, but they come with their own uncertainty. So one thing you could say is, if dark matter annihilated to the BB bar, then I'll not only get prompt photons, which are the things you see in that spectrum, but I'll get charged particles, which will then synchrotron radiate, and maybe I can look for that. And so people try to do those analyses. But even there, you have problems, because you have to say, well, now I've got to know the magnetic fields in the galactic center in order to figure out the synchrotron. So do I know those? Do I know those any better than I know the millisecond pulsar luminosities? So, yeah.
Another question. When you say the word excess with respect to what?
So you have these background models. So you say, okay, let me give you examples. You say, okay, I've modeled sort of diffuse isotropic emission. And so the way people will do this, they'll say, okay, I know what are the processes which can produce these things. I can produce pions. When cosmic rays interact with gas, I have these gas models. I have cosmic ray models. I have propagation models. I throw that all into Galoprop, and it gives me some model for isotropic, for these kind of diffuse processes in the Milky Way. I have some isotropic emission model, which I can say is dominated by extragalactic stuff. So I have some model for extragalactic stuff, and I can just extrapolate that into the galactic plane, because I shouldn't care about the galactic plane. Then I have the Fermi bubbles, and then I make some model for the Fermi bubbles. And I can say, okay, I've got all these models, and now I say, is there an excess of beyond what these models predict? And that's what the galactic center excess is, and it's about 10%. So the energy in the galactic center excess is about 10% of the Milky Way. Of what you predict from these background models. So it's not statistical. So it's not a statistical fluctuation. It's with high statistical significance you see this. But again, that could just mean you don't have the background models right. So maybe you didn't. Maybe if when I say you don't have the background model right, some contribution could be from mismodeling these backgrounds. Another could be to say, if I think about millisecond pulsars, there's another astrophysical background which I just didn't include. Then I need to include that. Okay. Or I can treat that as the source of the galactic center excess. But either way, that's kind of what's meant by the excess. Compared to these models for the background, with high statistical significance, you say that there's something beyond these models which is generating the galactic center excess.
So when we say mismodeling the background, does it mean mismodeling more in the isotropic part or anisotropic part? Is there a distinction?
Well, it could be both. The isotropic, you kind of say, well, I think it's coming from extragalactic stuff. There's no reason why the plane should be any different. It could be that there's some extragalactic stuff in the distance, right? Where for some reason there's something along that line of sight which you didn't see. For the anisotropic part, it could just be that, okay, maybe your gas model is wrong. So you didn't understand the gas targets for cosmic rays to hit, or you didn't understand the cosmic ray density right. Okay, all this you plug through galprop, or you make certain assumptions. Maybe those assumptions are wrong in galprop. Maybe you didn't have the right diffusion length or things like that. So there's an industry of people who work on trying to refine these models. Excuse me? Oh, the Fermi bubbles? I'm not sure they exactly know the mechanism. I think I honestly don't know. I shouldn't say anything because I'm not really an expert. I think they have a lot of ideas of what causes it. I think it, from essentially lepton emission from the galactic center or things like that. Astrophysical processes emitting from the galactic center. But I'm not sure if they have an exact handle on it.
Some people speculate that jets.
Mm-hmm. Excuse me? So these Fermi bubbles, I guess they're like some bubbles of, I don't know how to describe it. You can imagine if you had the galactic plane like this, and this is like the galactic center, there's some bubbles which are kind of like this, which are regions where there's extra galactic center emission.
This is also some kind of anisotropy.
Yeah, so this is kind of anisotropy. It could be incorporated into that model, but that model doesn't incorporate that because the kind of processes they involve, like again, it's, I have cosmic rays striking gas and producing pions or things like that. I have synchrotron radiation from such things. Those kind of templates don't include this emission. So this is often sort of added as a separate template.
So this electric center access, there is a difference between pulsar and this. So can it be nailed down using GW high frequency gravitational waves? Like because pulsar will give us continuous gravitational wave which would lie like in the cosmic explorer or that frequency.
Okay, so if you have this many millisecond pulsars, can you tell that you had that much from gravitational waves? That's beyond my knowledge of gravitational waves, observatories. But I mean, basically, I'm not just saying if I had between 1,000 and 30,000 millisecond pulsars, could I tell that I had that? And I don't know. I mean, just personally, to me, it seems like if I can't see it in gamma rays, I wouldn't imagine I could see it in gravitational waves. But then again, what do I know about it? So.
So wouldn't the gravitational waves be stochastic? And how do you know that if they're coming from those pulsars or the other source of the gravitational?
In this source frequency is roughly also the same.
Wouldn't that have a frequency like a source of
Yeah,
gravity?
they will have some frequency, right? Because the source mass is fixed. So that mass would basically correspond to the frequency of cosmic explorer.
Are you talking about the orbit of a millisecond pulsar with its binary? Okay. But even if you saw that, all that would tell you is that you had a bunch of millisecond pulsars. It wouldn't tell you that that produced a gamma ray center excess. Because you still wouldn't know what their luminosity is in gamma rays. But it would still tell you had a lot of them, right? Which would be a good step. I think, if people understood that there were definitely a lot of millisecond pulsars in the galactic center, then that would influence a lot of how people, how likely it was that you could have a millisecond pulsar origin to this. But again.
The GW observation sort of tests that this is the rough number and that number matches with these many pulsar can be plus
It could be from 10 order 1,000 to 10,000 or 100,000 even, but yeah, again, it would depend on being able to nail down how many of those are in the galactic center. So. And which are luminescent gamma rays. Because I think the issue is that you can have a lot of pulsars, but they won't necessarily be luminescent gamma rays.